So very good evening, friends. So today is a second class. I want to say, for example, this intensive revision program as such. So my dear friends, today we'll be discussing or we'll be taking the topics of climatology. Yesterday's, that is last class, we have tried somewhere covering the larger aspects of geomorphology. So in today's class, as I said, we'll be discussing about this very important topics on climatology. See, we have devoted two classes for climatology because preliminary examination, this chapter climatology is very important. When I talk about the questions on physical geography alone, if I just take it, climatology alone accounts for somewhere around 30 to 35 percentage of the question that has been asked in the past. If that is the case, climatology is very important. That's the reason two classes, revision classes, I'm devoting it for climatology, my dear friends. Right, and in between, just want to bring it to your notice that a full-fledged online program is available on Unacademy platform. You can make use of the same. And apart from that, my dear friends, the students who are preparing for this year's preliminary examination 2023, on 21st of May, there will be an 8 hours special marathon for current affairs alone. The most important topics for current affairs, continuous 8 hours, there will be a continuous session. And apart from that, on 12th of May and 13th of May, we have 3 hours and 3 hours put together, 6 hours of special marathon for CSAT topics, and mostly those topics which is important for the preliminary examination that will be given more emphasis and focus. And on 14th of May, we also have 8 hours marathon session, almost spreading across 5 subjects, 5 core subjects: geography, polity, economics, environment, history, and most important MCQs, multiple choice question for this year's preliminary examination shall be discussed. Right, my friends. So with this piece of information, starting with the climatology, what are the likely topics that we'll be seeing today? Like yesterday, today also I am just focusing on 7 topics. Season cycle, one of the most repeated questions, right, will be asked from season cycle. At least the last 3 years, twice the question has been asked from the season cycle. Then we'll be talking about this origin, evolution, and composition, along with the structure of atmosphere. We'll talk about insolation and distribution, incoming solar radiation, and how exactly this insolation is distributed. That also we'll be discussing. Then we'll be talking about atmospheric temperature. And when I talk about atmospheric temperature, we'll try to somewhere bring that relation between insolation and the terrestrial radiation, the incoming solar radiation and the outgoing terrestrial radiation in the name of heat budget. And apart from understanding the heat budget, we'll also talk about atmospheric temperature and the distribution of the same. We'll also talk about the concept of temperature inversion. And finally, today's class will be taking and concluding with atmospheric pressure and pressure belts of the world. Okay, right. Now, my dear friends, these are the likely topics, as I said, what we are going to discuss about. See, first, let me start with the season cycles. See here, if you ask me what exactly is a season, if you ask me season, see, for example, without explaining, right, or somewhere, if I say what exactly is a season, my dear friends, right, if I say season, I'll give an example. Season, summer is a season, right, winter is a season, right, summer is a season and winter is a season. We do, yeah, we have an understanding that summer and winter is a season, right. Now here comes the question, what do you mean by summer? What exactly is the defining character of summer? If you ask me, summer is known for longer days, my dear friends. It is known for longer days. And what about winters? Winters are known for longer nights. Okay. Either I can say winter is known for longer night, or I can also say that it is known for what? Shorter days. Right? Both way it is possible. Shorter days. Correct. So whenever I just talk about season, my dear friends, what do I understand by season, if you ask me? Right? Season is all about the temporal variations in the length of the day and night. Okay, that's what you call them as what? Season. Now the question is that what is the causative factor for season? What causes summer? What causes winter? See, the entire Earth together do not cause, right, do not experience summer or winter. Together, they don't experience summer or winter. Summer or winter is hemisphere specific. See, when I say hemisphere specific, say for example, if northern hemisphere experience summer, assuming that northern hemisphere it is experiencing summer, then the southern hemisphere will be experiencing what? Winter. Always there is a compensation between what? The hemispheres. Always northern hemisphere and southern hemisphere there is a compensation. Okay. It means if northern hemisphere experience longer day, it will be at the cost of southern hemisphere. That's the general idea. Okay. Now, having said that, having understood what exactly is a season cycle, and my dear friends, if you ask me, what causes season, right? What is the reason for season, right? There are two reasons which is cited for having what? Season cycle, my dear friends. If I just talk about reason, there are two reasons. Number one, the very important reason is what? Tilt of Earth. Tilt of Earth, right? And very important, my dear friends, I'm just integrating with this word called as and. It is tilt of Earth and what? Revolution, right? It is revolution, correct? It means both are very important. What exactly makes it a cycle is revolution. What facilitates, say, for example, northern hemisphere is experiencing longer days and southern hemisphere experience longer day during the different parts of the season or the year is the tilt of the Earth, right? Now here I can understand, somewhere I can see this image that Earth is tilted, right? When I talk about the revolutionary orbit, with respect to the revolutionary orbit, Earth's axis of rotation is tilted. Tilted by how many degree, if you ask me? It is tilted by 23.5 degree. See, it makes an angle of 66.5 degree. That's a different story, right? But what exactly is the tilt, right? What exactly is the angle by which the tilt happens, right? It is tilted by 23.5 degree, right? This is very important. And my dear friends, what I understand, because of this tilt, what happens at one point of time, northern hemisphere gets tilted maximum towards sun, right? When northern hemisphere is getting tilted maximum towards sun, during the same time, what happens? Southern hemisphere starts facing away from the sun, right? It starts facing away from the sun. When it faces away from the sun, I understand my difference. Somewhere, the difference in the length of day and night changes. For example, whenever one hemisphere is tilted towards the sun, somewhere you can see that length of the day is always more than what? Length of night. Okay. See here in the season cycle, I have given you the reason. What exactly is the season I said? What is the season? The temporal variation in the length of the day and night. During the different parts of the year, you call them as what? Season. The variation. At one point of time, you experience longer days. Another part of the year, you experience what? Shorter days. Why this changes, or what exactly this changes, you call them as what? Season cycle. And what is the reason? The causative factor. Two reasons I have given. Both are very important. I have integrated with this word called as and. Right? Not or, and means both are equally important. Tilt of Earth, along with that, revolution. Okay, right. So here I'm just giving you four very important days of a season. Number one, June 21st. Very important days. Very important day, my dear friends. June 21st. You call them as what? Solstice. June 21st, you call them as what? Solstice. Similarly, December 22nd also we call them as what? Solstice. We call them as solstice. June 21st and December 22nd, both we call them as what? Solstice. Solstice is that day when the hemisphere actually, say for example, one particular hemisphere, it gets, or it is, say for example, having the maximum tilt towards the sun or away from the sun. For example, June 21st, I'll understand that northern hemisphere will be having the maximum tilt towards the sun. This is the peak summer day of northern hemisphere. Peak summer day. See, when I say summer, summer means longer day. It means peak summer means what? Longest day. June 21st is regarded as the longest day in northern hemisphere, right? And when I talk about, say, for example, June 21st, because it is peak summer day in northern hemisphere, the solstice is generally called as summer solstice. And because December 22nd is a peak winter day in southern hemisphere, sorry, excuse me, northern hemisphere, This December 22nd is called as winter solstice. It is called as winter solstice, right? June 21st, you call them as summer solstice, and December 22nd, you call them as what? Winter solstice. One small clarification here. If examiner do not describe the hemisphere, if examiner simply says summer solstice of summer solstice, is not mentioning the hemisphere. If he simply says, if he or she simply says that it is summer solstice, then he or she is somewhere pointing to what? June 21st. Okay. If he or she simply says winter solstice, then the day what is being referred is what? December 22nd. But the examiner very clearly says summer solstice of southern hemisphere, then it is not June 21st, rather it is December 22nd. Solstice means, somewhere I understand, either it can be summer or it can be winter, but the peak day of the respective season. If they say it is a summer solstice of southern hemisphere, right? I understand whenever southern hemisphere experience the peak summer, northern hemisphere will experience what? Peak winter. Correct? In that way, when I talk about summer solstice of southern hemisphere, it means December 22nd. So what is the point I want to make it here? I'll tell you. If the hemisphere is not mentioned, the reference hemisphere will be northern hemisphere. If hemisphere is mentioned, read it with the said hemisphere. Okay, right. So my dear friends, when I talk about summer solstice and winter solstice, I understand summer solstice is that day when northern hemisphere has the maximum tilt towards the sun. Winter solstice, northern hemisphere faces maximum away from the sun. This is one aspect. Number two, these are the days when the sun's vertical rays reaches the maximum possible latitude. For example, June 21st, it reaches this latitude called as Tropic of Cancer. December 22nd, it reaches this latitude called as Tropic of Capricorn. 23.5 degree north and 23.5 degrees south. Okay. And I should also understand that these are the two latitudes which marks the northern and southernmost extension of sun's vertical rays. It means the places which is located beyond the Tropic of Cancer and Capricorn, beyond the tropical region. Tropic to tropic is what you call them as what? Tropical region. Tropic of Cancer to Tropic of Capricorn. This region you call them as what? Tropical region. It means only tropical region will experience what? Sun's vertical rays, not the other places of the earth. Other places of the earth will always experience slanting sun's rays. Always. Always experience slanting sun's rays. And of course, see, when I say slanting sun's rays, only thing is that never you will experience the phenomena called as vertical sun's rays. Never you will experience a phenomena called as head sun position. Normally, we ask ourselves a question, right? What do you mean by noon? Immediately people will say that noon means sun above your head. Let me tell you my difference. All part of the earth, all days of a year, you will not experience sun's vertical rays. Even when I say sun's vertical rays as a phenomena is applicable only to tropical region, right? That too, one latitude, only one day you will be experiencing it. Or at least I say, barring the exception of Tropic of Cancer and Capricorn tropical region, any place within this Cancer and Capricorn, if you're placing yourself, only twice a year you will experience the sun's vertical rays. Only twice a year. Okay, right. Right, my friends. Now, June 21st is very important day, my friends. Very important day. That's the reason I have just given this June 21st very separately. And I have also somewhere diagrammatically shown that what do you mean by the sun's vertical rays. See, for example, when I talk about sun's vertical rays, mark a tangent. The sun's rays is falling and making an angle of 90 degrees, you call them as what? Sun's vertical rays. To mark a tangent, always I'll be understanding if you're there in higher latitudes, I'll be having what? The lower degrees as such. Okay, right. So somewhere, what is this vertical sun's rays? What is this oblique or slanting sun's rays? We have an idea. Okay. Now here, coming back here, June 21st, I said it is very important, right? June 21st is very important. Right. We talk about this June 21st, my difference. What exactly happens on June 21st? I'll tell you. June 21st, you regard as summer solstice. It is the peak summer day of northern hemisphere. Peak summer day of northern hemisphere. It means it's the longest day of northern hemisphere. Okay. Now on this day, where exactly the sun's vertical rays will be falling, if you ask me, Tropic of Cancer, vertical sun's rays. Okay, vertical sun's rays. Beyond this, say for example, latitude, I will never experience sun's vertical rays as such. Right. Very carefully, if you see, my dear friends, as you move north of equator, as you move north of equator, the length of the day, you compare it with the night, day and night. If I just compare, the length of the day slowly and steadily stay, for example, they start increasing. It means right at equator, what I experience is 12 hours of a day. As I move north, somewhere, Tropic of Cancer, I experience the length of the day to be somewhere around 13.5 hours. As I further move north, slowly, steadily, Arctic region, it becomes 24 hours of light, daylight. It means on this day, entire Arctic region experience 24 hours of daylight, right? It means on this day, sun will not set in Arctic region. That's what very popularly you refer it as what? Midnight sun. See, name itself says, geography is one subject where the name itself says what exactly the concept is all about most of the time, right? Midnight sun means what? Even during the midnight, the sun will be there in the sky. If you want to go to bed, you want to sleep, right? Somewhere you have to look at your watch and you have to go to bed. Okay, midnight sun. That's the reason. Even we have a country called as Norway, right? Norway is called as what? Land of midnight sun. Because Norway is one of the other countries in the world which is there in what? Arctic region. Totally, there are 8 countries, including Norway. But Norway has used this word or this name before others would have used it, right? Even USA is there because of Alaska. Canada is there. Denmark is there because of Greenland. We have part of Iceland, Norway, Sweden, Finland, Russia. 8 countries are there. But still, Norway is called as land of midnight sun. See the beauty, my dear friends. Whatever I have seen for northern hemisphere, you exactly take the opposite. That is for southern hemisphere. Northern hemisphere, you increase the sign of latitude, or as you move, you increase the latitude, the length of the day increases. But here, what happens? The length of the day decreases. Whenever the length of the day is more than the length of night, you call them as what? Summer. If you're there in any part of northern hemisphere, it is summer. But winters, when I talk about southern hemisphere, length of night is more than the length of day. That is nothing but what? Winter. It means entire southern hemisphere, what it experiences what? Right? Right at equator, it is 12 hours of a day. Tropic of Capricorn, my dear friends, it is 10.5 hours. And Antarctic region, 0 hours. One place, 24 hours. Sun is not setting. Sun is not going below the horizon. Here, the sun is not rising. See the beauty. Right? One place, sun is refusing to go down. Another place, sun is refusing to come up. Always there is a compensation. Always there is a compensation. Okay. For examination, my dear friends, at max, what I have to remember, what happens on June 21st, right? With respect to northern hemisphere alone, you remember. Every other factor you can recollect it there. Okay. At max, what I have to remember is only June 21st, northern hemisphere. Right? December 22nd, what happens? Exactly opposite. Correct? Where the sun's vertical rays falls, Tropic of Capricorn. Exactly opposite. As you move towards north, the length of the day slowly, steadily decreases. The length of the day is less. You call them as what? Same thing. Right at equator, it will be, excuse me. Right at equator, it will be 12 hours of day and 12 hours of night. Once you're there at Tropic of Cancer, it will be 10.5 hours of daylight. As you reach Arctic region, my dear friends, Arctic region on this day I can see it is only 0 hours of daylight. 0 hours of daylight. And whereas, say, for example, I'll be having 24 hours of night. Exactly opposite. Correct? Exactly opposite. 6 months before, what you have seen is 24 hours of daylight and 0 hours of night. 0 hours of night. But here, what you're experiencing is completely different. Always there is a compensation. See, any place randomly you choose it in this earth. If I'm not including the concepts of twilight, refraction, and all, on an average, All days you take it. Length of day and length of night you take it. You'll be finding on an average it will be 12 hours of day, it will be 12 hours of night. This 12 hours of day, my dear friends, summer it will be increasing, I understand. But whatever increases is equally reduced during what? Winters, right? So that way, somewhere I have to remember it. Okay. Right, my dear friends. Now, as I said, only June 21st, you remember, that should be more than enough. And apart from that, see here, in between, we have two other important days. These days are days of transition, where summer eventually becomes winter and winter eventually becomes summers. Day of transition. Day of transition occurs either on March 21st, right? One on March 21st, another on September 23rd. All the days you take it, approximately every day you take it, approximately, my dear friends, they have a difference of 3 months, approximately. December 22nd. See, all these days, 23rd, September 23rd, there is a chance that I may experience this phenomena on September 22nd also. Nobody can deny it. Okay. But approximately you have a difference of about 3 months, right? 3 months. 3 months. So once one date I remember, rest of the dates I can remember. And what about this March 21st and September 23rd? We call them as what? Equinox position. Equinox literally means equal length of day and night. Equinox is the day where sun's vertical rays will be falling over equator. The entire earth, including the poles, will be experiencing 12 hours of day and 12 hours of this March 21st, my dear friends. Because Northern Hemisphere experience spring as a season during that time. Either you call them as what? Spring equinox, or you call them as what? Vernal equinox. Whereas when I talk about September 23rd, you call them as what? Autumn equinox. Right? You call them as what? Autumn equinox. My dear friends, season cycle is very important. If at all, if you want to remember this fact, just remember June 21st, that should be more than enough. Right? Now, having talked about season cycle, going to the next topic, right? Climatology itself is study of atmosphere. Okay. So first we'll understand what exactly is atmosphere, how this atmosphere had its origin, whether this atmosphere went for any evolutionary process or not, like landforms, we'll try to understand. And as of today, what are the different layers we have an atmosphere, and what exactly this atmosphere is composed of, the major composition of this atmosphere, somewhere we'll discuss about. Okay, right. Now, what is atmosphere, my dear friends? See here, normally we say the layer of air that surrounds Earth is called as atmosphere. It's a layer of air. And normally, my dear friends, it extends up to the height of 10,000 kilometers. Normally, extends up to the height of what? 10,000 kilometers from the surface of the Earth. Right? So, layer of air that surrounds Earth, you call them as what? Atmosphere. Normally extends up to the height of 10,000 kilometers, not even meters, 10,000 kilometers. Okay. See, though I say it extends till the height of 10,000 kilometers, right? Somewhere I say, I can also see here. From the surface of the earth, I can extend this till 10,000 kilometers. Okay. Though I say 10,000 kilometers, later I'll understand that, say, for example, the first 32 kilometers from the surface, my difference, first 32 kilometers. This first 32 kilometers itself occupies somewhere around 99% of atmosphere. It occupies around 99% of atmosphere. Remaining, say, for example, 9,968 kilometers contributes only 1%. We'll talk about it. It means first 32 kilometers itself, your near complete atmosphere is over. We'll just talk about the same. Right. Now we'll talk about this origin, evolution, and once again we'll talk about what structure of this atmosphere. Origin. What led to the formation of atmosphere is this process called as degassing. What is degassing? Emission of gas from Earth's interior. See, in geomorphology, we would have studied something called as sorting, sometimes also referred as differentiation. Sorting or differentiation. Gravity based arrangements, we call them as what? Sorting. Gravity based arrangement. Either you call them as sorting or you call them as what? Differentiation. Now, here, my dear friends, when I talk about sorting or differentiation, what is the sorting or differentiation? As I said, gravity based arrangement. All heavy elements will start descending towards the bottom of the earth, and the light elements will be starting ascending towards what? The surface of this. So, what happened? Gas being very light also started moving towards the surface of the earth, and gas being furthermore, say for example, light intensity, this gas started escaping. Okay, gas started escaping. And gas escaping from the surface of the earth is what very popularly we call them as what? Degassing. Right? Gas, talk about this gas, was traveling towards the earth's surface and gas started escaping. This gas started escaping, we call them as what? Degassing. Even today, when volcanic activity takes place, what gets emitted is what? Among the, apart from the magma, apart from the pyroclast, apart from volcanic ash, what gets emitted is what? This gas. Water vapor is the most commonest gas among them. Okay, so that gas escaping from the surface of the earth is called as degassing, and this gas which was escaping did not ultimately escape the gravitational attraction of the earth. It was retained back by the gravitational attraction of the earth. Right. So what led to the formation? Degassing. And my dear friends, this degassing is followed by the second stage called as condensation. Assume that water vapor went for degassing. And my dear friends, only this when water vapor goes for a condensation, right? It has to go for what? Condensation. Okay. And once it goes for a condensation means gas becoming, say for example, liquid, solid or liquid or solid, you call this process as condensation. So what happens? Post degassing that has taken place, all this gas went for condensation. It formed to the formation of cloud, and cloud resulted in what? Precipitation. See, that's how you remember. We talked about yesterday's class. We talked about this Alfred Wegener's continental drift theory. Then we talked about a supercontinent called as Pangaea. What led to the formation of Pangaea? We have an idea. Right? What led to the formation of Pangaea is somewhere the solidification, right? The solidification of this earth. That led to the formation of Pangaea. Solidification of the outermost layer. Right? And where exactly the Panthalassa came from? Panthalassa came from this process called as condensation. Degassing is followed by condensation. Condensation, all this water vapor became cloud. And the precipitation, continuous precipitation is the one which has resulted in the formation of what? Panthalassa as an ocean. So where exactly the ocean came from, if you ask me, the condensation as a process is what? Very, very important. And my dear friends, one of the later stages, only we had the development of free oxygen. What was dominating the primitive atmosphere, early atmosphere, was carbon dioxide. Carbon dioxide was more, and oxygen were almost negligible. It was only traces in what you find what? Oxygen. So today what happened? Slowly, steadily, carbon dioxide content started increasing. See, that time, almost the majority of atmosphere was dominated by carbon dioxide. Oxygen were almost nil. When I said nil, I should call it as what? Traces. Only a small amount of oxygens were, right, almost identified. But what has reduced the carbon dioxide? What has reduced the carbon dioxide of atmosphere and eventually also side by side increased the supply of oxygen is the life on earth, particularly when I talk about flora. Flora played a very, very important role in bringing down the level of carbon dioxide and increasing the oxygen content in the atmosphere. Okay, vegetation, the process of photosynthesis. Am I right? Only thing is that they acted as a carbon sink. See, artificially, if we start capturing the carbon, atmospheric carbon, and somewhere store it in non-atmospheric form, you call them as what? Carbon sequestration, right? If not carbon sequestration, this carbon capturing was done by this, say, for example, this floral activity. Vegetation played a very, very important role. Okay. And I'm just insisting the fact today oxygen content is somewhere around 21 percentage, my dear friends, and this 21 percentage happens to be one of the highest in the known history of the world as such. Okay, right. So what is atmosphere? We have an idea. What are the stages that is involved in origin and evolution of atmosphere? Both we have taken it. Again, I am insisting development of free oxygen only came at the later stage. Only came at the later stage. Okay. Then comes the evolutionary process. Do sun play any role in somewhere making a change in Earth's atmosphere? If you ask me, answer is yes. In that way, I should understand. In yesterday's class also, we talked about these two sets of planets. Terrestrial planets versus Jovian planets. Terrestrial planet and Jovian planets, two very important things I have to take it. Jovian planets, outer four you call them as Jovian, inner four you call them as what? Terrestrial. Both are separated by the belt of asteroids. When I talk about terrestrial planets, I understand terrestrial planets are smaller ones, whereas Jovian planets are larger ones. So somewhere we also believe that it means the gravitational attraction of Jovian planets will be larger than the gravitational attraction of what? The terrestrial planet as such. And I also know the fact terrestrial planets are very close to what? Sun. Whereas Jovian planets are located comparatively far away from the Sun. So given all the factors, my dear friends, somewhere we have an idea, we have an understanding, right? That somewhere if I have a very strong wind from the sun is getting emitted, solar wind, right? If the solar wind gets emitted, okay, if I have the solar wind that is getting emitted, the solar wind has the potential, right? Solar wind has the potential to somewhere modify the atmosphere of these terrestrial planets also. Okay, in the sense, the idea says Mercury, when I talk about Mercury, my dear friends, Mercury hardly has any, say, for example, atmosphere as such. So the solar wind, powerful solar wind, has the potential to remove the atmosphere of Mercury. See, Earth also substantially, the solar wind also modified this Earth's atmosphere, but complete removal so far we have not experienced. But Earth being a part of terrestrial planet, right? Say, for example, there is a larger chance that even solar wind would have played its own role in modifying the Earth's atmosphere as such. Okay, right. Now, with this piece of information, my dear friends, okay. So, somewhere we talked about the evolution, right? Evolution of this atmosphere. After talking about this evolution of atmosphere, we'll also talk about this composition, right? What exactly this, excuse me, right? What exactly this atmosphere is composed of, okay? What they are composed of. See, in that way, the major composition, I can divide them into major and minor composition. See, I have just given some of the values also. I'll make this value slightly in the rounded off figures, right? I'll make it in the rounded off figures, right? In that way, my dear friends, in that way, when I talk about this entire atmosphere, the constituent can be divided into major constituents and minor constituents, right? Major and minor constituents. So what is a major constituent if you ask me? Nitrogen is the single largest gas, right? Entire atmosphere, nitrogen occupies 78% of this Earth's atmosphere, nitrogen. The distant second, we have in the name of what? Oxygen. Oxygen occupies somewhere around 21%. It means two gases alone occupies what percentage of atmosphere if you ask me? Two gases alone occupies a 99 percentage, my difference. 99 percentage. It means near complete atmosphere, right? And okay, remaining 1% collectively I call them as minor constituent. In this minor constituent, my dear friends, 1%, which is the single largest gas if you ask me, argon. When talk about argon, argon occupies 0.93 percentage. It means three gases in atmosphere alone occupying how many? Right. What percentage of atmosphere, if you ask me, it is occupying 99.93 percentage of, right, the entire atmosphere. So all the gases and constituent remaining, if I just take it, remaining what I have is only 0.07 percentage. Only 0.07 percentage. Okay, right. Now, why I want to insist on this fact, I'll tell you, my dear friends. Because when I talk about, say, for example, this major constituents, right, versus minor constituents. These major constituents, I have just given you three major constituents as such. These three major constituents alone, if I just take it, right, they are stable, but they are inactive. They are inactive. It means they do not have any climatological role, right? They are stable, right? They are stable. Their distribution is uniform. Wherever you are collecting an air sample, right? Everywhere the distribution is uniform, but they are inactive. It means they do not have any climatological. On the other hand, when talk about the minor constituents, my dear friends, minor constituents. Okay. Among the minor constituents, the most important minor constituents is carbon dioxide. Approximately, carbon dioxide has a composition of somewhere around, say for example, 0.036 percentage, right? Has a composition of somewhere around 0.036 percentage. Okay. And comes the question, when I talk about 0.036 percentage, it appears to be very, very small in percentage. But carbon dioxide play a very important role when it comes to determining the climate of this Earth as such. Okay, we'll talk about the role of carbon dioxide. Apart from that, we also have ozone, right? And carbon dioxide and ozone, they are stable. See here, what is the contextual meaning? Forget about the actual meaning of stable. Here, when I use this word called a stable, somewhere I'm just trying to tell you that the distribution of these gases are more or less similar, right? More or less. Okay. When I talk about it, means whether you somewhere select an air mass from India or USA or Canada, the content of carbon dioxide is going to be more or less similar. That's the reason there is a hue and cry against carbon dioxide emission. Whichever country is emitting carbon dioxide, that country alone is not going to get suffering. Means almost it is not going to get, right? Almost it is not going to suffer from this emission because given the nature it is stable over a period of time, the distribution will become what? Uniform, right? They're active, they're also stable. But when I talk about water vapor and aerosols, my dear friends, they're active, but they're unstable. Unstable in the sense, from place to place, their distribution will vary. Okay. So this composition of this atmosphere is important. Okay. But here, I've just given you only the four major gases by percentage. If you want to go beyond it, it is also worth noting other gases and what exactly is their share in the atmosphere. Okay. See, all these values, you forget it. Don't even take this value because I understand. Mostly it is given in ppms. The share becomes very less. It gives it what? Right. Almost say, for example, it becomes in what? Ppm. Parts per million. Okay. Not given in percentage as such. Okay. So it is worth noting going beyond carbon dioxide emissions. Neon, helium, krypton, xenon, and hydrogen. Okay. Gases, if I just go beyond major four, it is neon, helium, krypton, xenon, and hydrogen. In examination, most of the time, try to put hydrogen at last. Okay. Mostly it will be working as such. Okay. Now, we talked about atmosphere. We talked about the origin of atmosphere. We talked about the evolution of atmosphere. We talked about the composition of atmosphere. And now we'll be talking about the structure of atmosphere. How exactly this atmosphere looks like. Okay. In that way, when I talk about this atmosphere, my different structure, this atmosphere has a different layers. At least I can take it as a 5 different layers, right? The lowest layer, we call them as troposphere. Just above troposphere, we have stratosphere. The middle layer, we have mesosphere. Earth's interior also, we had a layer called as mesosphere. Above mesosphere, we have thermosphere. And above this thermosphere, we have what? Exosphere. Okay. So these are the, say for example, layers, what we have in atmosphere. See this order very easily, you can remember it. For example, any middle layer, you call them as mesosphere. And the outermost layer, we call them as what? Exosphere. Of course, the layer in which we are living, we are interacting, what is called as weather layer of the earth, we call them as what? Troposphere. But somewhere, feel that, okay, I may forget this in examination. Maybe you can remember in this way, right? Something like that. Trust me in the exam. When I said trust me in the exam, TR is troposphere, ST is stratosphere, ME is mesosphere, TH is thermosphere, EX is exosphere. Okay, not needed, but worst case scenario, I'm just telling you, right? How exactly I can remember these layers as such. Okay, now coming back here. When I talk about atmosphere, I said atmosphere extends to the height of 10,000 kilometers, but it is open-ended. It means you do not have any clear-cut demarcation that this is the place where exactly atmosphere is coming to an end. Okay. As you increase the height, this atmosphere becomes rarefied. Okay, in that way, my dear friends, though you are extending till 10,000 kilometers, as I already said, first 32 kilometers itself occupies a 99 percentage of atmosphere. Just 32 kilometers. It means 32 kilometers, 99 percentage, remaining 6,000, 9,000, 968 kilometers, if you take it, only 1%. Whether you take the height of atmosphere as 1,000 kilometers or 10,000 kilometers, it is not going to make much difference as such. Okay. Right, my friends. Having said this, the lowest layer, troposphere, do not have a uniform height. Just above this troposphere, we have stratosphere, which is often called as ozonosphere because there's a layer where we have the presence of ozone. Then above this, we have mesosphere, middle layer. Then the thermosphere, sometimes I also refer it as ionosphere, and the exosphere as such. Now, one by one, if I just take it, and the upper limit of any layer, we name it as what? Pause. We call them as what? Pause. So, troposphere, right? The upper layer, you call them as what? Tropopause. Stratosphere, the upper layer, you call them as what? Stratopause. Mesosphere, the upper layer, you call them as what? Mesopause. You call them as what? Mesopause. Okay. Right, my dear friends. In that way, when I talk about troposphere first, see, as I already said, troposphere, you call them as what? Weather layer of the earth. And it is the largest layer by mass, my dear friends. Largest layer by mass in the sense, majority of atmosphere is confined to what? This troposphere. Majority is confined to troposphere, right? And on the other hand, I should also understand this is the smallest layer by volume. A volume, if I just take it, it is the smallest layer. Okay. Obviously, I understand if both the facts comes together, I can understand that this layer will be the densest layer. Okay, right. And see, when I say weather layer of the earth, whatever changes that takes place in this layer, that is what we call them as what? Atmospheric condition. It is not the condition prevailing in the entire atmosphere. No. The condition what prevails in what? The lower atmosphere, the lowest atmosphere. Okay. Right. Now, this troposphere do not have that uniform height. They do not have uniform height. Tropopause, to be very precise, they do not have uniform height. At one place, it is 18 kilometers and one place only 8 kilometers. So where exactly I will be having the maximum height? It is over equator. Why? Because equator, the temperature on a daily basis, it is higher. So throughout the year, what I will be experiencing is a rising convection. When the air mass rises continuously, rising convection, this air mass will be pushing this tropopause beyond its original limit. That's the reason why exactly I have this maximum height. Whereas on the other hand, polar region, my dear friends, somewhere the tropopause will be subsiding because what you experience throughout the year is what? Subsiding convection. Minimum height, 8 kilometers. Okay. So one thing, it gives you an idea. See, okay. Locationally speaking, polar regions will experience the minimum height and equatorial region will experience what? Maximum height. That is okay. If this is the logic, my dear friends, let me also tell you. Even the same place, I just take it and differentiate it between winters and summers. The height of troposphere or tropopause during summer will be higher, winters will be lesser. Okay, right. And my dear friends, when I talk about this troposphere, the most important property of this troposphere, if you ask me, this most important property, we call them as what? Normal lapse rate. So what is this normal lapse rate? Generally we say, if you increase the height, the temperature generally what? It decreases. Increase in height will result in decrease in temperature. Okay. You increase the height, what happens? Temperature decreases. This phenomena, you call them as what? Normal lapse rate. See, for example, why hill stations are colder? Normal lapse rate. All right, simple. Right. As you increase, for example, as you fly, in the flight, normally the pilot says the outside temperature is what? Somewhere. Say, for example, it is less. When they say the outside temperature is less, minus 30 degree, minus 40 degree, they say, why? Because normal lapse rate. Okay, whatever is the case, you increase the height, temperature decreases, right? This property of this troposphere, very popularly, you call them as what? Normal lapse rate, my dear friends. Now here, why exactly you experience normal lapse rate, I should understand. For example, I should understand how exactly this atmosphere is getting heated up, if you ask me. The rays that comes from the sun, you call them as insolation. This insolation will penetrate the atmosphere and largely this insolation will be heating up the surface. I'm not saying insolation will not heat up the atmosphere, but insolation will be largely heating up the surface of the earth, right? Largely. Whereas the heat that is liberated from the surface of the earth in the name of terrestrial radiation is the one in turn heats up the atmosphere, that too not directly, with the help of greenhouse gases. Okay. So if you ask me in that way, how exactly atmosphere is being heated up? Actually, atmosphere is heated up from the bottom, right? From the bottom. Bottom means what? From the surface of the earth, right? Atmosphere is heated up from the surface of the earth as such. That's the reason. As you move away from the surface, the temperature comes down. Because the immediate source of atmospheric temperature is this source called as terrestrial radiation. The heat that is liberated from the surface, you call them as what? Terrestrial radiation. That's the immediate source. Okay, right. So normal lapse rate is the most important property. So one thing I know, you increase the height, temperature gets reduced. At what rate? Every 1 kilometer of increased height, the temperature will get reduced by 6.5 degree centigrade. Right, my dear friends. Now, in that way, entire troposphere, I understand, you increase the height, temperature will get decreased. So in that order, if somebody is asking you, where exactly the minimum temperature is recorded in entire troposphere, it is recorded at tropopause level. That is okay. But since tropopause level itself is not having uniform height, where the minimum temperature is recorded, if you further ask me, very interestingly and surprisingly, it is over equator. Not over equator, it is a tropopause level over equator. It means from equator, I have an altitudinal difference or a height of 18 kilometers. This is a place where the minimum temperature in the entire troposphere is recorded. Very important fact. Very, very important fact. Okay. So that's all about troposphere, my friends. Then stratosphere. See, stratosphere, you call them as ozonosphere, my dear friends, because this is the layer where you have this concentrated ozone confined. So here generally what happens, my dear friends, once you increase the height, the temperature also increases. Why? It is all because of presence of ozone. Also you can write it as O3. How ozone? Very simple, because see, ozone, we call them as what? Ozone, I know the fact that ozone will be filtering what? It will be filtering the harmful ultraviolet radiation. Okay, it will be filtering this harmful ultraviolet radiation. So somewhere I understand ozone will be absorbing this insolation. See, ultraviolet radiation is the other name for insolation. You call them as short wave radiation. You call them as what? Ultraviolet radiation, or you call them as what? Insolation. All are same. So what happens, assuming that the first stage of filtration of insolation happens in ozone. Assuming that 100 percentage of insolation somewhere reaches this ozone. What comes out of ozone is only 86%. Only 86%. It means 14% is absorbed by what? Ozone. Plus symbol here, I'm just denoting somewhere absorption. 14% is absorbed. Okay, right. Now, my dear friends, because I do not have normal lapse rate, and let me tell you, normal lapse rate is very, very important, because only if I have a normal lapse rate, this normal lapse rate generally results in cloud formation. It will be resulting in the process called as condensation. If normal lapse rate is not there, generally clouds are not formed. So, one fact I know about this troposphere in the sense, sorry, stratosphere. Stratosphere is relatively free from clouds. Just because it is relatively free from cloud, my dear friends, it is relatively free from clouds. This layer is the most preferred layer for what? Aviation industry. Okay, right. Now moving to the next layer, mesosphere. Any middle layer? Any middle layer, we call them as what? Mesosphere. So I talk about mesosphere, my dear friends. One thing I understand, you increase the height, temperature decreases. See, till mesosphere, the larger source or the major source of atmospheric temperature. Till mesosphere, it is terrestrial radiation. So till mesosphere or mesopause, as you increase the height, the temperature should get reduced. But the only exception being what? Stratosphere, and that too, where in stratosphere? Only the place where I have the presence of ozone. There is no ozone, I will not experience this. Like for example, I'll put spirit. Only the place where I have the ozone, I'll be experiencing normal lapse rate. If you do not experience normal lapse rate, if the temperature increases with increasing height, that phenomena we call them as what? Temperature inversion. So temperature inversions is experienced only because of what? Presence of ozone. Okay. Now here again, mesosphere also, I experience a kind of normal lapse rate. Kind of a normal lapse rate. The rate at which the temperature is decreasing may be different, but temperature is decreasing. If that is the case, here also I may have cloud formation. And these clouds, we call them as what? Noctilucent cloud. Noctilucent cloud. Okay. See, and this noctilucent cloud, they may not result in precipitation. Very, very thin fibrous clouds will be having. Sometime during the astronomical twilight, you may witness this cloud. But they may not have much of climatological relevance. And how come this cloud got their formation somewhere between this 50 to 80 kilometers of height, if you ask me? Maybe the moisture would have been majorly sourced from the, say for example, an asteroid or a meteoroid which enters the Earth. And here, my dear friends, the very important layer, this layer we call them as what? Ionosphere. One small clarification. I am treating ionosphere and thermosphere, both are same, but small clarification. If I take it as ionosphere, ionosphere extends from 80 kilometers to 400 kilometers. Whereas thermosphere extends from 80 kilometers to 700 kilometers. It means 80 to 400 kilometers, it's both ionosphere and thermosphere. And beyond this 400 kilometers is only this thermosphere. If that is the case, there is a greater degree of overlapping. Then why exactly I have chosen it as ionosphere, I'll tell you my difference. Because we experience one geographical phenomena here in this layer. For example, what exactly is that phenomena? Because the name itself says ionosphere, and it is an electrically charged layer. So whenever an electrically charged particles from the sun gets emitted, assume that, say for example, right, the solar wind gets emitted. As and when, say for example, the solar wind tries to enter this Earth's atmosphere, of course we have a magnetosphere that will be deflecting it. It acts as a shield. Okay. But though I say it is getting deflected, I understand these deflecting solar winds or deflected electrically charged particles from the sun will be attracted towards the polar regions. Attracted towards the polar region. And I understand this layer itself is what? Electrically charged layer. It means ionosphere will also have electrically charged particles. So what happens here? It happens only in the polar region. When the electrically charged particles of the sun and electrically charged particles of this ionosphere, when they go for a collision, this collision will produce a light. And that light produced, you call them as what? Auroras. What you can see here in this image is more an aurora, right? It is more an aurora, right? Something, it looks like a laser light show high in the sky. One of the most beautiful phenomena what you can see here in the sky. You call them as auroras. And auroras happens only in the polar region. You may ask, why only in polar region? Very simple. Why exactly this deflected winds or solar winds is getting attracted towards the polar region, if you ask me? Because polar regions are the place where I have the magnetic poles confined. Today, where exactly North magnetic pole is confined to, if you ask me, it is confined to Canada. Canada, there is an island called as Baffin's Island. To be very precise, Queen Elizabeth Island, Canada. Somewhere I understand, right? All these electrically charged particles will be somewhere attracted towards this place where exactly Earth's magnetic field is very high. So where exactly Earth's magnetic field is very high? Polar region. That's the reason these auroras, we also call them as what? Polar lights. It's a light. We call them as a polar light. And of course, it happens in northern hemisphere, Arctic region, as well as in what? Southern hemisphere. So auroras of the northern hemisphere, you call them as northern lights. Technically speaking, you call them as what? Aurora borealis. You find a forest in the backdrop. You ask me what exactly is the name of this forest. The name of the forest, you call them as what? Taiga forest. Sometimes you also call them as what? Boreal forest. Either you call them as taiga or you call them as what? Boreal forest. That's the reason. This aurora, you call them as what? Aurora borealis. Right. And similarly, when I talk about southern hemisphere, from the southern parts of Australia, you can witness this from Tasmania. Right. So you call them as what? Southern lights or aurora. You call them as what? Aurora australis. Okay. Right. And my dear friends, when I talk about this ionosphere, that is thermosphere, including exosphere, you increase the height, the temperature also increases. Name itself says thermosphere. It means this is the most hottest layer or the warmest layer. The maximum temperature is actually recorded in what? Thermosphere only. Now we may have a doubt. What is this? You are saying that maximum temperature is recorded in thermosphere. But most of the satellites are confined to thermosphere. Yes. See here, I'll tell you what. How to understand this temperature. Assume that you are an astronaut. You are there in the International Space Station. International Space Station is confined to thermosphere. Most of the low Earth orbits are confined to what? Thermosphere. So you want to check this temperature. So somewhere if you are putting your hand outside this International Space Station to check how hot the temperature is about, you will not feel anything. You will not feel anything. Because I understand, say for example, you need a medium to absorb that heat. But once you put your hand outside for an extended period, just to check that how hot it becomes, sometimes that will be the last time you will be seeing your hand. Okay, because it becomes very hot. Somewhere it has reached, the temperature has reached up to 1600 degrees centigrade also, provided you have a medium which continuously absorbs this insolation. Okay, so whatever be the case, an entire atmosphere, which is the warmest layer, if you ask me, the warmest layer is thermosphere. Right? The warmest layer is thermosphere. Right, my dear friends. Now, basic facts about Earth's atmosphere also we have taken it. And consolidated fact. All the layers with their property, I have just somewhere noted it. Troposphere, what happens? Temperature versus height, if I am calculating it. With increase in height, temperature decreases. Stratosphere, what happens? The temperature increases. Mesosphere, what happens? Temperature decreases. Thermosphere, what happens? Temperature increases. Now, in that order, where exactly maximum temperature is recorded? Somewhere in thermosphere, right? On the other hand, if somebody is asking where exactly the minimum temperature in entire atmosphere is recorded, very important fact, it is at mesopause level. It is at mesopause level. It is a place where exactly, right, the minimum temperature is recorded. Not even tropopause level, it is at mesopause level. Okay. Right, my friends. This is all about the structure of atmosphere. Right. Now moving into the next topic, insolation. So two topics out of these five topics, two topics we have covered, and both the topics are the larger topics. The rest of it is not so large a topic. See, insolation. What is insolation? Simple. The name itself says it is incoming solar radiation. Maybe I'll put this way, right? It is incoming solar radiation. That's what you call them as what? Insolation. Or layman's understanding, you call them as what? Solar energy. The trace amount of heat that Earth as a system receives from the sun. You call them as what? Insolation. It is defined as the thermal radiation that Earth receives from the sun. The amount of heat that Earth as a system receives. From where? From the sun. You call them as what? Insolation. Okay. See, my dear friends, this insolation is more or less static throughout the year, but barring an exception of perihelion and aphelion. You know perihelion, right? When I talk about perihelion, generally perihelion occurs on January 3rd. It occurs on January 3rd, perihelion. And when I talk about aphelion, January 3rd. When I talk about aphelion, my dear friends, aphelion generally occurs on July 3rd or July 4th. Okay, July 4th, remembering is very easy because American Day of Independence, something like that. Okay, whatever it is the case, right? Normally, insolation received by Earth is more or less static, barring this exception of perihelion and aphelion. And my dear friends, though Earth as a system receives is almost static, but the distribution of insolation will vary from place to place and time to time. See, place to place means between lower latitudes and higher latitudes, this insolation distribution will be different. Same place between summer and winter, the insolation distribution will be different. Okay. So here we'll talk about this distribution of insolation. What are the factors which affects the distribution of insolation? Number one, very, very important, angle of sun's rays. At what angle the sun's rays falls. In that way, see, for example, I'll take it this way. Assume that somewhere I am there in the tropical region, maybe equator, equinox day. Sun is rising at 6 a.m. Slowly, steadily, the sun is climbing. Reaching a point above my head, the time is 12 noon. And slowly, steadily, say for example, the sun is descending and reaching the horizon again by 6 p.m. Sun is setting at 6 p.m. Sunrise 6 a.m. Noon, zenith position, sun above my head, 12 p.m. And again, slowly, steadily, the sun is coming down, reaching the horizon, right? Somewhere I understand it is 6 p.m. again. Right? In that way, when I talk about the angle, every time the sun makes a different angle. For example, rising sun makes an angle of 0 degree. Slowly, steadily, it will climb. Noon sun, it will make an angle of 90 degree. Again, the angle at which the sun's rays is falling. Somewhere you can imagine, right? Angle at which the sun's rays is falling. Anywhere it can vary between 0 degree to 90 degree. Rising sun and setting sun 0 degree. Just coming out of the horizon. Noon sun 90 degree, my difference, right? So this is what you call them as what angle of sun's rays. At what angle it is falling with respect to the surface of the earth, right? So normally binary classification, if the sun's rays is falling anywhere between 0 to 45 degree, we call them as what? Low sun position. The sun's rays is falling between 45 to 90 degree, we call them as what? High sun position. We call them as high sun position. Now, where all I can apply this logic, I'll tell you, my difference. Very easy. Latitudinally, I can apply this logic. For example, higher latitudes, polar region, throughout the year, I'll be experiencing the slanting sun's rays. Because I said, if you go beyond the tropical region itself, you will not experience vertical sun's rays. Always there is a slanting sun's rays. As you move away from this equator, the sun's rays will become more slanting, slanting, and slanting. Okay. So higher latitude, what normally I experience is low sun position. Lower latitude, what I experience is high sun position. So, my dear friends, what exactly happens here? When I talk about a comparative study, assume that I am just taking two rays, sun's rays of equal radius. Energy carried by this rays is more or less similar, but what makes the difference is distribution. At one place, this energy is getting concentrated, and another place, the energy is getting what? Distributed. Okay. One place energy is getting concentrated, another place the energy is getting what? Distributed. When energy is getting concentrated, the temperature will increase. When energy is getting distributed, the temperature will decrease. See, we have made that somewhere. That magnifying glass experiment also we would have done. Somewhere you will be focusing the sun's rays, concentrating on a piece of paper or a piece of cotton. Eventually you will burn them. What exactly is happening there is all about what insolation is getting concentrated. If insolation gets concentrated, obviously speaking, temperature will what? Increase. If insolation is getting distributed, the temperature will decrease. Okay? Right. Right, my dear friends. Now, having talked about this angle of sun's rays, angle of sun's rays, right. Now, where all it is applicable, I said latitude, latitudinally it is applicable. Okay? Lower latitudes versus higher latitude. Seasonally also it is applicable because the same season, summer I'll be experiencing high sun position, winter I'll be experiencing what? Low sun position. I'll show you, for example, same, somewhere diagrammatically if I can show that. Okay. Right. Summer and winter also there is what? A difference. For example, Bhopal, June 21st vertical sunrise. But same Bhopal, December 22nd, the maximum angle where the sun's rays can climb itself is only 43 degree. Why 43 degree? You forget about it. But summer and winter also I'll be having a difference. Summer I'll be having high sun position. Energy gets concentrated. Winters, low sun position. Energy gets distributed. Okay. And finally, my dear friends, even say for example, in a day also I can experience the same. Why noon is very hot? Because vertical sun's rays. Why say for example, almost morning and evening is not so great in temperature because of slanting sun's rays. Right? Right, my dear friends. Now, this is one angle of sun's rays. And number two, along with the distance, along with the angle of sun's rays, number two should be taken as a supplementary fact. Distance traveled by sun's rays through atmosphere. The word through is very, very important. See, for example, I am taking two rays. One is vertical sun's rays, another is slanting sun's rays. And assume that this is atmosphere. This is atmosphere. Normally, I find that this vertical sun's rays travel a short distance through atmosphere. Slanting sun's rays travel a longer distance through atmosphere. Now, normally, my dear friends, shorter is the distance traveled by sun's rays through atmosphere, less will be the loss of insolation. Less will be the scattering of insolation. Less will be the absorption of insolation by water vapor. Less will be the reflection of insolation by the clouds. So the loss will be less, right? Less loss of insolation. If the longer distance is traveled by insolation through atmosphere, more will be the loss of insolation. So by the time the slanting sun's rays reaches the surface, this rays will be a faint rays. So what do you understand by faint rays if you ask me? Largely devoid of energy. Much energy will not be there. Am I right? Normally we say, right? I'm feeling like fainting. It means I'm losing out my energy. Okay. So point number one and point number two, they are complementary to each other. Here I can see here. See, I talk about slanting sun's rays. See, for example, vertical sun's rays versus slanting sun's rays. See the distance traveled. This is the distance traveled versus the distance traveled here. See, 1 and 2 I can compare. Slanting sun's rays travel a longer distance, whereas vertical sun's rays travel a shorter distance. Okay, right, my dear friends. So, insolation distribution, two very important facts we have talked about. Number three, the length of the day also plays a very important role, because when I say longer days means what? Summer, longer days. The period of insolation, it means, for example, if I say summer, Tropic of Cancer, 13.5 hours the land will get exposed to the sun along with the vertical sunrise. All right. So longer will also be the period of what? Insolation. Longer will be the period of absorption. So the temperature will be on a higher side. Winters is known for shorter days and the lesser period of insolation. So that somewhere temperature will be somewhere coming down. Okay, right. See, one factor alone I should not take it. It is a combination of factors. Okay. This length of the days alone should not be taken. Along with the angle of sun's rays, I should also consider the length of the day. Only then the concept will be okay. Insolation is the primary source of heat for Earth as a system. Where exactly the energy comes from, if you ask me, sun. Okay. Though it is not heating up the Earth's atmosphere directly, but the primary source of atmospheric temperature is insolation. So we talked about the distribution of insolation. Now moving on to the fourth topic of the day, atmospheric temperature. In atmospheric temperature, first we'll talk about the heat budget. Right, my friends. Now we'll talk about this atmospheric temperature. Okay. Now see, when we talk about atmospheric temperature, amount of heat present in the lower reaches of atmosphere, we call them as what? Atmospheric temperature. It means what? The heat what is present in the lower reaches of troposphere. We call them as atmospheric temperature. And of course, I understand atmospheric temperature, the immediate source is terrestrial radiation and the indirect source, primary source is insolation. So first what we'll do, before talking about the distribution of this atmospheric temperature, we'll talk about the relation between this insolation and terrestrial radiation. Okay. Already say, for example, we talked about the same thing. Right? Somewhere we talked about the same thing. Earth's, the heat or the insolation primarily heats up the surface of the Earth, and the heat that is liberated in the terms of terrestrial radiation is the one which is heating up the Earth's atmosphere as such. Right? In that way, my dear friends, somewhere we'll talk about the relation that exists between insolation and terrestrial radiation. Insolation, my dear friends, either you call them as insolation, or you call them as what? Short wave radiation, or you call them as what? Ultraviolet radiation. Ultraviolet radiation, the wavelength is what? Short wave. That's what you call them as what? Short wave radiation. On the other hand, terrestrial radiation is also called as long wave because it is infrared in type. Infrared will be having longer waves, right? Wavelength as such. Sometimes this terrestrial radiation is also called as Earth radiation. You can also call them as what? Earth radiation as such. Now see, when I talk about this heat budget, my dear friends, assume that we have sun, right? And assuming that 100% of insolation comes, see, this is just for a number. Just for our understanding, I am taking it as 100%. I am not even putting it as percentage. 100 units is coming from sun. And here, all this plus what I am using is for absorption. It is absorption. Minus is for loss. Plus is for absorption. Okay. Plus is not addition and minus is not subtraction by difference. Plus is absorption. Minus is loss. Okay. Now here, out of the 100% that comes to Earth's atmosphere, I understand, already we have seen, 14% is absorbed by what? Ozone. So what is remaining? 86. In that 86, 6% is scattered by aerosol. That's the reason normally when the pollution is more in atmosphere, the temperature will be less. The day after Diwali, you can find it normally. Sun will be finding it very difficult to penetrate. Okay. So scattering, aerosol scatters sunlight, insolation, and reduces 6% of insolation. If it is that, what is remaining is only 80. And in this remaining 80, my difference, nearly 27% is reflected by cloud cover. Whenever insolation is reflected back, whenever it is reflected back, this reflection of insolation, we call them as what? Albedo. We call them as what? Albedo. Okay. We call them as albedo. Reflection of insolation, we call them as what? Albedo. Right. And say, for example, in 80, another 27 is gone. What is remaining is only 53. So, right, this 53% finally reaches the surface of the Earth. Even in this 53%, what happens, my dear friends? The ground object will be reflecting this insolation again by 2%. Particularly ice caps. Ice caps plays a very, very important role. Okay. So 53, 50, another 2 is gone. What is remaining is what? Only 51%. In political terms, we call them as what? Simple majority. Right? What exactly reaches the surface of the Earth is only nearly half of the insolation. Nearly half of the insolation is somewhere it is lost. Only 50% or 51% of the insolation is finally absorbed by the surface of the Earth. Am I right? And in between, my difference, already I said, I talk about reflection of insolation. Wherever insolation is getting reflection, very popularly you call them as what? Albedo. See, technically, albedo, meaning it is slightly complicated, but that much is not needed. The nature of the surface, the color of the surface plays a very important role in determining this albedo factor. Everything is completely reflected back. Normally, we say that albedo fraction is what, somewhere around 1. But normally, see, white color will have more albedo. Why glaciers are having more albedo is because of the color. And even smoothness. But it's very shiny surface, again the albedo factor will be more. Okay. See, that's the reason even some pilgrimage site, particularly the right, wherever you are going to a pilgrimage site, where normally the temperature becomes very hot during summers. And somewhere if the footwears are not allowed to somewhere explore the places, there all you'll be finding some white stripes here and there. Once you start walking in these white stripes, slightly the temperature will be on a lesser side. If you ask me what exactly is the principle is very simple: albedo, reflection of insolation, right? White color, yellow color, and all. The albedo factor is what? Okay. Now here, what are the various constituents in atmosphere which reduces the temperature or reduces the insolation? Somewhere we have taken it. In that way, my dear friends, coming to the aspect of glaciers. Now about glaciers, glaciers plays a very important role. When I say glacier playing a very important role, okay, I'll put it this way, right? For example, I know the fact that global warming, today we are talking about global warming. Okay, I'm talking about global warming, right? When I just talk about this global warming, my dear friends, I understand one thing: global warming will be resulting in deglaciation, right? Glaciation. What is deglaciation? All these glaciers being removed, you call them as what? Deglaciation. So I know the fact that global warming results in deglaciation. Not only me, everybody knows. But what is very interesting, will you accept the fact if I say deglaciation will further increase the global warming? It is a vicious cycle. See, for example, tomorrow if all the glaciers are removed in this world, tomorrow, Earth will not start absorbing 51 percentage. Earth will start absorbing 53 percentage of insolation. It means the temperature will increase, right? See the vicious cycle. Global warming will be melting the glaciers away, deglaciation. The deglaciation will further increase the temperature of the earth as such. Global warming can be resulted further. See this very easily you would have cited here. 2020, what happened during the period of COVID? Amazon forest was somewhere burning. That burning of this Amazon forest had an influence in melting the large scale Greenland glacier. Global warming. If it is not a global warming, it is a regional warming resulted in what? The melting of regional glaciers. Global warming resulted in deglaciation. The very next summer, what happened, my dear friends? Adjoining Canada started experiencing heat dome or heat dome. Exceptionally higher heat or, say, for example, warm condition, Canada started experience. If you ask me what can be the reason, very simple. The deglaciation of Greenland glacier has resulted in somewhere, right, making Canada slightly what? Vicious cycle. See? Okay. Now it's a very, very important fact. All that reduces the insolation we have taken. And on the other hand, when I talk about terrestrial radiation, okay, all this 51 percentage is somewhere emitted back into the atmosphere. And that 51 percentage is 17 percentage is directly, right, escapes or directly, say for example, almost it escapes to exoatmosphere. And what is remaining 34 percentage? This remaining 34 percentage is temporarily holded back by carbon dioxide. See, not only carbon dioxide is represented by all, say for example, all these greenhouse gases, right? Greenhouse gases represented by its gang leader called as what? Carbon dioxide. Okay, 34 percentage. And see what exactly is the composition of carbon dioxide. 0.036 percentage of carbon dioxide is holding back 34 percentage of insolation. This is 1/3 of insolation, and it is nearly 2/3 of terrestrial radiation. What I assume that it is very, very small, 0.036 percentage is holding back 2/3 of terrestrial radiation. That's the reason we say even the marginal increase in carbon dioxide may somewhere substantially modify the heat budget of the world. Substantially, it can modify the heat budget of the world. Okay. And see, my dear friend, see, for example, in that way, it doesn't mean that carbon dioxide is a demon. No. There is no need to demonify this carbon dioxide. Carbon dioxide is a very essential gas, very, very important for sustaining the life. See, if carbon dioxide would have not been there, we will not be here. Very important because primary producers needs carbon dioxide. We need primary producers. Assume that we are primary consumers or secondary consumers. Food chain is determined by the primary producers as such. Okay. Now, forget about this primary production as an activity. Role of carbon dioxide. How important is carbon dioxide, my friends? Carbon dioxide is very, very important because if carbon dioxide would have not been there, my friends, if carbon dioxide would have not been there, the temperature of the earth would have been colder, right? If no carbon dioxide, earth would have been colder by 33 degrees centigrade. It means today, the average temperature of the earth is somewhere around 15.2 degrees centigrade. If no carbon dioxide, my dear friends, no carbon dioxide, the temperature of the earth would have been somewhere around minus 18 degrees centigrade. See the difference. So carbon dioxide plays a very important role in maintaining the temperature of the earth. Not only that, carbon dioxide plays a very important role in maintaining night temperature. If carbon dioxide would have not been there, right, all this 51 percentage that is absorbed by the earth would have been readily liberated into the exoatmosphere. Night would have become what? Extremely cold. Day will be more or less similar, but night would have been become what? Extremely cold. So what helps in maintaining the temperature of the earth is carbon dioxide. Very important. Right? Very important. But only thing is that we have to maintain it within the permissible limit. Okay? Right. So this is all about heat budget, my dear friends. So post understanding the heat budget, now we'll talk about the distribution of this atmospheric temperature. Earth as a system we talked about. But this atmospheric temperature will vary from place to place and time to time. What are the various factors which actually affects the distribution of atmospheric temperature? Obviously, latitude, my dear friends. When we talk about latitude, see, I know the fact that you increase the latitude, right? You increase the latitude, the temperature decreases. Because I understand, you increase the latitude, insolation decreases, angle of sun's rays decreases, so the temperature decreases. Similarly, if you ask me, right, you increase the altitude, my dear friends, you increase the height or altitude, again the temperature decreases. Why? It is all because of normal lapse rate. It is all because of normal lapse rate. Okay. Then comes continentality or distance from sea. We'll talk about this continentality or distance from sea. For example, Chennai and Delhi, if I just take it, Chennai and Delhi. When I talk about Chennai, my dear friends, Chennai versus Delhi. During summers, which will be very hot if you ask me, obviously Delhi will be very hot in comparison with what Chennai. And similarly, if you ask me during winters, Chennai versus Delhi, which will be cold if you ask me, again Delhi. See, winter, when talk about, say, for example, Chennai do not experience true winters. That's the reason, very sarcastically, right? They say only 3 seasons are there in Chennai. Don't take it very seriously. They say only 3 seasons what you have in Chennai is only what? Hot, hotter, and hottest. Okay, whatever it is the case. There is nothing called as true winters for 2 reasons. The places which is located to equator, the difference in the length of the day between summer and winter is not so distinctive. And number two, influence of water. Water has the ability to maintain temperature. So the fluctuation of the temperature in the coastal areas will be comparatively less if you compare the places which is far away from the coastal areas. Right? That's what we call them as what? Continentality or distance from sea. Then even ocean currents and prevailing winds plays a very, very important role. And of course, local factors also plays a very, very important roles. Local factors like clouds, water vapor, aerosols, etc. So one by one, we'll see my difference. Right? What exactly is the difference that exactly it makes? For example, latitude, if I just take it. See, obviously, I understand you increase the latitude. What happens to the temperature? Temperature decreases. Why? Because insolation concentration itself what decreases. And just based on this latitude alone, my difference, just based on this latitude alone, Greek scholars has divided the entire Earth into different thermal zones. They have divided into what? Different thermal zones. The lower latitudinal region, tropic to tropic. See, for example, what we call them as tropical region, Greeks were calling it as torrid region. According to them, this region is very hot. Not even warm, they are saying very hot. And they say, for example, it is not conducive for ordinarily living condition, they say. But I should understand, say, for example, some of the most populated regions of the world are located in the torrid region. But okay, whatever it is the case, according to Greek scholar, it is very hot. Whereas what lies, say, for example, beyond this Arctic and Antarctic circle is a frigid zones, completely glaciated. And what lies between them is a temperate regions. According to them, it is moderate region. Right? They have also used this region as what? Warm condition. See, for us it is cold condition. For them it is already warm condition. Okay, whatever it is the case. What is the parlance we refer it? Torrid, we don't call it as a torrid. We call them as what? Tropical. We don't call it as a frigid. We call them as what? Polar region. And temperate, we also call it as what? Temperate. Now here, the point what I'm just trying to make it. This is one of the earliest climatic classification what they have done. And they have done it only taking into consideration of what? Latitude, nothing else. Only latitude. Okay? Nothing beyond it. Okay. Now, my dear friends, okay, this is one very primitive classification, but somewhere I'm telling you that, okay, latitude plays a very, very important role. Apart from latitude, my dear friends, even altitude plays a very important role. When I say altitude, you increase the height, the temperature decreases. Why? Normal lapse rate. And what rate it decreases? For every 1 kilometer of increased height, the temperature comes down by what? 6.5 degrees centigrade. Or I can also say, I can rewrite it, for every 165 meters of increased height, the temperature gets reduced by 1 degree centigrade. This is another way of saying. But actually, interestingly, if you convert this, you will not get it. These figures, you will not get it. But I am just taking the popular figures from the popular books, including NCERT. One source says every kilometer the temperature will get reduced by 6.5 degrees centigrade, and this rate of lapse is more or less uniform throughout the troposphere. Another source says every 165 meters 1 degree centigrade decreases. Approximately okay, right? It comes somewhere around 156 meters. Okay, no problem. 165 you can take it. Nothing wrong in it. So one thing I understand: normal lapse rate. Why normal lapse rate? I know the story because Earth's atmosphere primarily gets heated up from the bottom. Now, the third concept, my dear friends, continentality. What I was just talking with respect to Delhi versus Chennai, continentality. Distance from what? The sea. See, water maintains temperature. This term is very, very important. Water maintains temperature. What property of the water makes water to maintain temperature, if you ask me? There's three property. The translucent nature, mobility, and high specific heat capacity is the one which makes water to maintain temperature. The translucent character, the mobility, the high specific heat capacity. So what is what and all? See, going in depth is not needed. Only thing is translucent means transparent. When I talk about land versus water, land only the surface gets heated up, but water it is not like that. The entire volume of water gets heated up. Mobility, water is more mobile. And technically we say the specific heat capacity of water is very high. Technically we say the amount of energy needed to increase the temperature of water by 1 degree centigrade is more than what the land does such. Okay, that's what we say, high specific heat capacity. That can only forget. What is that I have to remember is only one statement or one sentence. Water maintains temperature. Fluctuation of temperature will be minimum in what? The oceanic regions. Right? Minimum in water means, say for example, oceanic region. And my dear friends, this is one of the reasons why Australian cities are confined to the coastal margins. Australian summers are very harsh because when I talk about Australian summers of Australia, right, very harsh. And every, say for example, every summers of Australia, my dear friends, what is very common is what? Forest fire. Talk about Australia, okay. When I talk about Australia, right, What is very, very common is what? Forest fire. Summers are very harsh. Why exactly summers are very harsh if you ask me? Because December and January is their summer. December and January, Australia experienced two things. One, already it is experiencing what? Summer solstice. Along with summer solstice, I should understand January 3rd is what? Perihelion position. See, already it is peak summer. Along with the peak summer, what is adding salt to the existing wound? The distance between Earth and Sun is also what? Very, very less. Right? That's the reason, my dear friends, Australian summers are very harsh. And that is one of the main reason why exactly the cities of Australia, you take it, all the cities, Brisbane, Sydney, Canberra, Melbourne, Adelaide, Perth, Darwin, all the cities you take it, you'll be finding that they are confined to what? Coastal margins as such. Because I know water maintains temperature. Fluctuation of temperature is not so great. Summers will not become so hot. Winters will not become so cold. It will be moderating it. But as you move away from the coastal areas, the land will behave purely like land. And of course, I understand the fluctuation will also be on what? Higher side. Okay. And I've also given you the comparative table, where I was just talking about the anomaly, temperature anomaly, right? Temperature anomaly between land and water. If you're there in lower latitude, generally because water maintains temperature, lower latitude land will be warmer than the water. Whereas higher latitude, very interestingly, I understand that it is not visible. Okay. So what I'll do, yeah, very important fact. Now it should be visible, right? Say for example, if you're there in higher latitudes, my dear friends, what I understand, water will be warmer than what? Land. Very important. This analysis is very important. This you can apply it for latitudes, or you can also apply the same for what? Seasons, right? Seasons. Okay. So both I can take it. Right. Water maintains temperature. Very, very important. I have just given you water maintains temperature. I repeat again. If you're there in lower latitude, I understand that land will be warmer than water, adjoining water, same latitudinal waters if I'm comparing. Whereas if I'm there in higher latitude, interestingly, water will be warmer than what? Land. Because water maintains temperature. Whenever I say warmer and colder, my dear friends, same latitude you have to somewhere compare. Do not compare between latitudes. It is within the same latitude you have to compare. Okay? Right. Right, my dear friends. Now, talking about the last local factors and ocean currents, right? Ocean currents and prevailing winds also plays a very important role. See, ocean current in that way, it is very, very important. Why ocean currents are very, very important, I'll tell you. See, ocean currents and wind plays a very important role in somewhere compensating the heat balance or somewhere balancing the heat balance of this earth. Few places insolation is stronger, terrestrial radiation is weaker. Few places it is vice versa. So somewhere for the longer sustenance, that heat balance has to be there. Somewhere from the surplus region, the surplus, whatever it can be surplus of temperature, it can be surplus of humidity, it can be surplus of salinity, it can be surplus of air mass, whatever it is the case, right? Somewhere it will try to bring it to the regions of deficit. So ocean currents and say for example almost the wind plays a very important role in at least transferring the heat, right, from the surplus region to the deficit regions. Plays a very, very important role. Now comes the question, what is the ocean current? Name itself says current. Any continuous movement of ocean water in a particular direction and for a sustained period, we call them as what? Current. Name itself says current. We'll be talking about current separately, but I'm just telling you, name itself, we call them as what? Current as such. Right? In that way, my dear friends. Now about ocean currents. Right? Now about ocean currents. I have plenty of ocean currents, but here I generally have two types of ocean currents based on temperature classification. One I call them as warm current, and two I call them as what? Cold current. Okay. I call it as a warm current and cold current. See, what is warm current? Are they defined according to the temperature? If you ask me, no, they are not defined according to the temperature. They are somewhere defined according to the, right, I put sugar, right? If it is warmer than the adjoining waters, I call them as what? Warm currents. If it is colder than the adjoining water, I call them as what? Cold current. Right? Warmer than the adjoining water, I call them as warm current. Colder than the adjoining water, I call them as what? Cold current. So there is no temperature that is defining what exactly is warm current and cold current. But currents generally, if you take it, right? Somewhere I am just, right, just for you, I'm just bringing it, right, making it as so visible, right? Slightly visible. And talk about this current, my dear friends, right? You find a pattern when it comes to the currents. You find a pattern. What is a pattern, if you ask me? Any ocean, if you're putting yourself, any ocean you take it, if you're putting yourself in the middle of any ocean, one thing you find, the western side of the ocean, I'll be finding warm currents, and the eastern side of the ocean, I find cold current. See, this is not universal. No concept in geography is universal. No concept is universal. But one thing I understand, right? Largely, this is applicable. We do have an exception, but largely, right? It is except means it is applicable. So how I can remember with respect to the ocean, I can remember that west is warm. West is warm. Okay. Somewhere I can remember that west is warm. Right. When I say west is warm, it is all about, say, for example, somewhere saying that western section of the ocean is what? That's it. And one more clarification, what is west of ocean becomes east of land. So any continent you take it, normally the eastern side of the land will come under the influence of warm current. Small observation, but very important observation. Very important observation. Okay. So I'm just giving you a slogan. What is the slogan? West is warm. And when I say west is warm, it is with respect to ocean, my dear friends. With respect to ocean, west is warm. Okay. Right. Right, my dear friends. Now, the basic idea we have taken it. Right. And of course, when any region, coastal area comes under the influence of a warm current will increase the temperature. Any region that comes under the influence of a cold current, it will reduce the temperature. And see, one fundamental idea. Whenever I talk about climate, climate as a concept is applicable only in land. The climate of the land can be influenced by ocean, but ocean as such, I do not have the concept of climate. So climate is applicable to the land as such. Only thing is that we are talking about the influence of this water in the land. Okay. And coming to the last, prevailing winds I have not discussed. Only thing is that prevailing winds. The winds are coming from the colder region, this wind will be cold. The winds are coming from the warmer region, this will be warm. As simple as this. Okay. We'll talk about the wind. When the wind as a fact, we take it. Now the local factors. For example, local factors, particularly when I talk about cloud, my difference. See, when I talk about cloud, we talk about cloud, my difference. Cloud play one very important role in the sense, we said cloud reflects insolation. Technically, we were calling it as what? Albedo. Right? Cloud reflects insolation. Right? When cloud reflects insolation, what we understand, right? When cloud reflects insolation. Normally, I understand if cloud are present in the daytime, it will be reducing the temperature. That is okay. But what is very interesting, my difference, if the same cloud is there during the night time, this cloud will increase the temperature because cloud can also reflect what? Terrestrial radiation. If cloud can reflect the terrestrial radiation, cloud can increase the temperature. That's the reason normally we say cloudy days will be colder than the cloudless days, obviously. But when I talk about cloudy nights will be warmer than the cloudless nights. For example, this condition, when I say morning, it should be free from cloud. The surface of the earth should have been heated. All of the sudden during the night time, very carefully watch the words. When I say all of the sudden during the night time, if I have a freshly formed cloud or some cloud has intruded, it will not allow the terrestrial radiation to escape. You're getting it? The terrestrial radiation is not escaping. The night will be warm. Okay. And very important, see, later also we'll connect it. Normally during the cloudy nights, my dear friends, cloudy nights, temperature inversion will not take place. Cloudy nights, dew or frost formation will not take place. All right. Later I'll be connecting it. So now what I have to understand, cloudy days will be colder than the cloudless days, whereas cloudy nights will be warmer than the cloudless nights. Okay. This I have to remember. Right. All right, my dear friends. Then the role of water vapor. Water vapor also plays a very important role. For example, daytime what happens? Water vapor will reduce the temperature because water vapor can absorb insolation. Nighttime, the same water vapor can increase the temperature because it absorbs terrestrial radiation. See, water vapor is also a greenhouse gas. Any gas, water vapor is a gas, right? Water in the form of vapor, water in the form of gas. When I say greenhouse gas, what is this greenhouse gas? Any gas that do not allow the terrestrial radiation to directly escape into the exoatmosphere, we call them as what? Greenhouse gas. Right? We call them as a greenhouse gas. It means water vapor is also what? A greenhouse gas. Okay. And finally, my dear friends, even aerosol play a very important role. Already we have seen, right? If you have presence of aerosol, all these are local factors. From place to place and time to time, they'll be different. Aerosol supply increases, temperature will decrease because aerosol will scatter insolation. If it scatter insolation, somewhere temperature will be reduced. The net insolation received by the earth itself will be what? Less. Okay. Right, my dear friends. Now, coming to the sixth topic of the day, temperature inversion. Only in troposphere. See, troposphere, what I experience in troposphere is normal lapse rate. What is normal lapse rate? You increase the height. As I increase the height, temperature will decrease. That is what you call them as what? Normal lapse rate. Accepted. But I understand there is a one situation. Somewhere we experience a situation in troposphere where you increase the height. When you increase the height, along with increasing height, the temperature also increases. See, not everywhere. See here, when I talk about, say, for example, this graphical representation, what I have taken, you increase the height, my dear friends, the temperature decreases. Correct? But when I talk about, say, for example, only one small place where you increase the height, with increase in height, if the temperature also increases, the small place, right? You call them as what? Temperature inversion. Temperature inversion is exactly opposite to what? Normal lapse rate. So what is normal lapse rate? When you increase the height, the temperature generally decreases in troposphere, right? This phenomena, you call them as what? Normal lapse rate. However, under certain circumstances, the temperature also increases with increasing height. This deviant phenomena is popularly referred as temperature inversion. See, temperature inversion is a very short-lived phenomenon, right? But still, I'm telling you what exactly is temperature inversion. Okay. Now, my dear friends, when I talk about temperature inversion, what is a normal condition? Normal condition, surface condition will be warm. Slightly you increase the height, upper air condition will be cool. Normal lapse rate. Warmer air, above this warmer air, I'll be having cooler air. Above this cooler air, I'll be having cold air. So you may wonder, what is this? Cold air will be less in density. Not this air. Not this warm air with respect to this air. Am I right? Okay. Okay, whatever it is the case. Only I'm just going with respect to what? Temperature as such. And temperature. Normally, this is how this condition, say for example, air mass will be arranged. Okay. You call them as a normal lapse rate. But temperature is a inversion is a condition where the ground condition will experience what? Cold condition. Above this cold air mass, what I'll be having is warm air mass. This layer we call them as what? Inversion layer. Okay. Warm air mass is placed above the cold air mass as such. You call them as what? Temperature inversion. So this image itself gives you an idea. The temperature inversion can be experienced, or it is very common, either during the colder regions, or either in the colder region or during the colder season. That's the reason. If you ask me where all this temperature inversion is very common, on a perennial basis, polar region. Because polar region experience cold condition throughout the year. Temperature inversion is very common in polar region. And which season, if you ask me, temperature inversion is common during long winter nights. Long nights itself means winter, but still I'm insisting this fact. Long winter nights, but very interestingly, cloudless nights. Cloudless nights. Why cloudless nights? Because I'm writing this cloudless nights because if clouds are there during the night time, what will happen, right? Somewhere I understand the temperature will increase, right? I'll not have cold condition if cloud persist because cloud during the night time will increase the temperature. What we need is a colder condition. Okay. So polar region and long winter nights, temperature inversion is very common. On the other hand, regionally, if you ask me one more region, mid latitudes, my dear friends. Later we can connect it, mid latitudes. Somewhere around the 60-degree latitude or this subpolar low. Subpolar low, very popularly you call them as what? Mid latitude. So mid latitudes also temperature inversion is very, very common. Temperature inversion is also common along the mountainous regions, mountains, right? Mountains. Wherever I have a tall mountains and a very deep valley, during the forenoon hours or morning hours, temperature inversion is very common. Okay. How in detail it is not needed, but somewhere these are the regions where temperature is very common. Polar region and mid latitude throughout the year. Tall mountains, very tall mountains. Along with the deep valleys also temperature inversion is very common. And long winter night, again I insist, long winter night, but cloudless nights. So these are the places and the time when exactly temperature inversion will be very, very common. And see, normally when temperature inversion takes place, winter and all, it is very common, my dear friends. And normally what happens during this winter condition, right, this temperature inversion normally results in, say, for example, something called as it traps the pollution. It will not allow the pollution to somewhere escape. Okay. And that's the reason, say, for example, if once the pollution enters this, right, this high pressure zone or a stable region, removing this, say, for example, this pollution, it becomes what? Very, very difficult. That's the reason. During winters, northern plains of India, the air quality becomes what? Very worrisome. Particularly during winter. Summer, you may not have that great problems. But winters. And that's the reason normally we say winters, one, say, for example, even the stubble burning in the adjoining states. Somewhere, if at all, say, for example, if the aerosols enters, say, for example, the Delhi atmosphere, removal of the same becomes what? Very difficult. Only if I have some precipitation coming in, right? The western disturbance comes in, only then, say, for example, some amount of, right, these aerosols can be removed. So temperature inversion condition may also result in, particularly during winters, it may result in something called as what? Pollution dome, right? Northern plains of India, this pollution dome is very, very common, particularly Delhi, right, my friends. So having talked about the temperature inversion, coming to the last topic of the day, atmospheric pressure. See here, what is a climate if you ask me? Climate is an atmospheric condition. What condition? See, for example, climate is a resultant atmospheric condition where I'll be talking about the atmospheric conditions of temperature and moisture. What determines the climate of a particular place? Temperature and moisture. Right. What determines the climate of a particular place, if you ask me? It is a wind. Wind plays a very important role in determining what? The climate of a particular place. Wind plays a very important horizontal movement of the air mass. Wind is the one which carries the moisture and delivers the moisture in a particular place. What causes the wind, if you ask me? It is pressure. Pressure is the causative factor. Pressure, I have two types of pressure in atmosphere, high pressure and low pressure, surplus region and a deficit region. Wind always moves from high pressure to low pressure. And what creates the pressure, if you ask me, it is atmospheric temperature. It is atmospheric temperature. And what exactly is the ultimate source of atmospheric temperature, if you ask me? The energy comes from sun. You call them as what? Insolation. So one by one, what exactly we are studying in climatology? We have taken the concept of insolation. Then insolation resulted atmospheric temperature we talked about. Insolation and atmospheric temperature, they are directly proportionate to each other. Now we are going to talk about temperature resulted what pressure and what exactly is the relation they have, generally inversely proportionate. Generally, we do have an exception, but generally they are inversely proportionate to each other. Okay, higher temperature, lower pressure. That's what the idea is. Having said what exactly is the relation, my friends. Now, when I talk about atmospheric pressure, what is atmospheric pressure? See, atmosphere has a weight, and this weight of atmosphere will be acting on the surface of the earth. Where exactly it will be falling? It will be falling on the surface of the earth. So, that weight exerted by the atmosphere on the surface of the earth is what we call them as what? Atmospheric pressure. The weight of the air column being exerted on the surface of the earth, we call them as what? Atmospheric pressure. So, in that way, if you ask me what exactly is the average atmospheric pressure, average atmospheric pressure stands at 1013.25 millibars. 1013.25 millibars. Average pressure. Slightly greater than 1 bar. 1 bar means barometer. Right? Bar is a unit for measuring pressure. 1 bar is equal to 1000 millibars. Okay. So somewhere I understand it is slightly greater than 1 bar. Okay. 1013.25 millibars is the average atmospheric pressure. So normally, so any system which has a value of more than 1013, I call them as high pressure. Less than 1013, we call them as what? Low pressure. Okay. And when I talk about high pressure, if it is large in size, not so intense, you call them as what? Wedges, or you call them as what? Ridges. Okay. Whereas when I talk about, say, for example, high pressure, which is slightly intensified, you call them as what? Anticyclone. Whereas when I talk about low pressure, my dear friends, low pressure, not so intense, but large in size, we call them as what? Trough. Very intense. You call them as what? Cyclones. Cyclone is very important for us. Tomorrow's class in detail we'll be discussing about this cyclone. Okay. Right, my dear friends. So somewhere, when I talk about pressure, the high pressure and low pressure, what exactly is the difference? Somewhere I have just taken it. Now, first, what we'll do, today's class we'll be doing, what exactly we'll do? We'll talk about the troughs and wedges of the world. All the troughs and wedges of the world are taken together. That's what we call them as what? Pressure belts. Totally, there are 7 pressure belts in the world. We are going to discuss about these 7 pressure belts of the world. 7 pressure belts. Very easily you can remember it. Only 4 names you take. What are the 4 names? Equatorial low pressure, subtropical high pressure, subpolar low pressure, polar high pressure. Right? 4 in the northern hemisphere and 4 in the southern hemisphere. Equatorial region being common to both, or equatorial low being common to both. Totally we have 7 pressure belts. These are the major 7 pressure belts of the world. Major 7 pressure belts. Right now, only thing is that I have to first, I'll go for remembering. How to remember the names first, I'll take it. Okay. Then we'll talk about how exactly they are formed. When I talk about, say, for example, this remembering very different. See, for example, equatorial region, the name itself says equator. 0 degree. 0 degree, I have equatorial. 0 degree is equator, the pressure is low pressure. Why exactly the pressure is low pressure? Because equatorial region experience high temperature, the pressure is low pressure. Okay, only equatorial low I have to remember. Rest, see, 30 degrees. 30 degrees slightly beyond tropics. Tropical region ends at 23.5 degree. So slightly beyond the tropic, you call them as what? Subtropic. Low becomes high, right? Then 60 degrees. 60 degrees is slightly beyond the polar region. So you call it as what? Subpolar. And again, high becomes what? Low. 90 degrees polar region, right? And low becomes what? High. There is an alternate sequence of pressure system. Every 30 degree you travel north and south, low will become high, high will become low. I repeat again, equatorial region, low pressure. Slightly 30 degrees, slightly away from tropical region, subtropic, high pressure. 60 degrees, slightly beyond polar region, subpolar, low pressure. Polar region, high pressure. Okay, alternate sequence of low pressure and high pressure we have. Now see, I can understand one thing. Why polar region experience high pressure? I have a logic. Why equatorial region experience a low pressure? I have a logic, because they are created by what? Thermal efficiency or thermal character. You call them as what? Thermal direct pressure belts. Polar region, temperature is extremely cold. If that is the case, pressure system created will be what? High. Whereas equatorial region, temperature is what? Higher. So the pressure system created will be what? That we have an idea. That's the reason polar high and equatorial low, my dear friends, both these pressure systems, we call them as what? Thermal direct pressure system. We call them as what? Thermal direct pressure system. Whereas subpolar low and subtropical high, my dear friends, this high pressure and low pressure is created not because of temperature effectivity, they are created by the mechanical action. Mechanical action. There are two reasons that is cited for this creation, right? If you ask me what exactly is the mechanical action, the most important reason cited is what? Rotation of the Earth. That is a mechanical action. And the distance exists between the polar high and equatorial low is also, say for example, seen as that reason for this difference. Okay. So somewhere I understand mechanical action is the primary reason why exactly these two pressure belts are created. And that's the reason subpolar low and subtropical high, they are called as thermal indirect pressure belt. Not necessarily that every time only the temperature is the one which is resulting in what? Resulting in the development of a pressure, right? Even we have thermal indirect pressure systems, right? So equatorial low and polar high are thermal direct pressure systems. Subpolar low and subtropical high, they are thermal indirect pressure system. If you ask me which is more, somewhere I'll put it this way, right? Which is more permanent, which is more stable, if you ask me, right? Which is more permanent. It is thermal direct pressure systems or what? More permanent in nature. Okay. Thermal indirect pressure systems are more temporary in nature. Here itself you can see. I'm comparing these pressure systems. You can find both thermal direct and thermal indirect. Both you can find it somewhere here. Fine. For example, first I'll show you this equatorial. What you're seeing here, all this gray shaded or light blue shaded region is equatorial. Whether you be it in the month of January or July, what I understand, I'll be having this continuity of these pressure systems. But when I talk about subtropical high, my dear friends, subtropical high, northern hemisphere, see, northern hemisphere, subtropical high, the month of July, they can confine only to what? Oceanic regions, Atlantic Ocean and Pacific Ocean. Very technically, we call them as what? Aleutian high and Hawaiian high. The high pressure which is created in Atlantic Ocean, you call them as what? Aleutian high, named after one island there. So here in Pacific Ocean, you call them as what? Hawaiian high, because Hawaii Islands are there. Okay. But the same pressure belt during winters, January you see, it becomes what? Like a belt. See the kind of an oscillation, right? Similarly, when I talk about subpolar low, January, again getting confined, one in Atlantic Ocean, one in Pacific Ocean. You call them as what? Icelandic low and Aleutian low. But the same in winters you see, sorry, excuse me, in summers you see, it gets spread over all the latitudes as such. So what I'm just trying to say is very simple. This much technicality is certainly not needed. Not necessarily temperature alone creates a pressure system. Pressure system is also created by what? The thermal indirect effectivity or the mechanical actions as such. This is number one. Not necessarily by temperature. Even mechanical action can create what? The pressure system. The rotation of the Earth is the primary reason which is cited as creating the two intermediate pressure systems as such. Thermal direct are more permanent. Thermal indirect have this oscillatory trend. Okay, that's what the basic difference is all about. Okay, but again, knowing the names or these names of this, say for example, this pressure system, 7 pressure systems are there, 4 names, remembering the names and approximate latitude is very, very important. I repeat again, equatorial region, equatorial loop. You're there in 30-degree north and south subtropical region, it is subtropical high. 60-degree latitude, what is called as mid-latitude, right? Subpolar regions, you experience a low pressure called as subpolar low. In polar regions, we have polar high, right? Now see, this pressure belt is very important because between the pressure systems are the one where I have the planetary winds that is flowing. Between these 7 pressure belts, I have 6 planetary belts. In one hemisphere, let me take it as 3 planetary belts, right? You call them as what? Northeastern. Forget about it. Trade winds, westerlies, and polar winds. Okay. So remembering the pressure systems are very, 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 very important. And of course, these pressure systems has a nicknames also. Equatorial low, otherwise popularly called as doldrum. The region where you normally do not experience much of wind. The windless region and equatorial belt, you call them as what? This 30-degree north and south, popularly you call them as what? Horse latitude. So you have a history, a small anecdote behind naming this latitude as horse latitude, but since it is being this intensive revision program, going for an anecdote is not needed. The subpolar low is called as mid latitudes. So these are the other names for exactly, these are the other names for, right, the latitudes as such. These are the nicknames of the latitudes. Okay. So this is very, very important, my dear friends. Very, very important. Okay. Right, my dear friends. Now, here it brings the end of today's class. All the 7 topics, climatology, somewhere we have developed a gist. Okay. So tomorrow, the rest of the climatological topic, we'll take it and we'll discuss, right? So thank you and God bless. So keep preparing, go for more revision, avoid learning things very new, right? Altogether new, because only somewhere around, right, slightly more than a fortnight's time is there for us. Go for a constant revision, practice more MCQs, and try to solve all the past year's question first and go more for MCQs. Okay. Wishing you all the best and God bless. Thank you.